And thank you for joining us in another lecture with my DARS series. Where's my notes? That is the worst in this case. Okay. We're thrilled to welcome two esteemed researchers from the Professorship of Digital Design and Fabrication, abbreviated as DDF, at Karlsruhe Institute of Technology, Daniel Fischer and Erik Zanetti. Both are the forefront of pushing the boundaries of computational design, sustainable materials strategies, and circular construction methods, critical areas shaping the future right now. Before we begin, I'd like to introduce our guest speakers, Daniel Fischer, and hi. Daniel Fischer, architect with a strong background. Maybe I could bring this start. An architect with a strong background in digital design and circular construction, joined DDF in 2021 after working as a project architect. His research focuses on digital wood construction and the integration of digital circular economy principles, addressing the urgent need for more sustainable building approaches. Erik Zanetti, a research assistant at DDF, brings a vast knowledge in circular building systems and material innovation. With expertise in bio-based waste and earth materials, he combines digital techniques with hands-on fabrication strategies. His experience as a computational designer and digital fabrication specialist at, help me here, FIBR GmbH.
Freiberg GmbH, yeah.
How do you say that?
Freiberg GmbH.
Okay, that's hard. Further enriches his research with industry expertise. Today, Daniel and Erik will share their insights into the cutting-edge advancements in digital fabrication and sustainable material strategies. Their work is relevant and timely as the architecture field seeks to transition toward more resource-efficient and circular building practices. Thank you, Erik and Daniel, for your time.
Thank you. Thank you for the invitation. So as you know now, I'm Erik, this is Daniel, and we work at the Professorship for Digital Design and Fabrication that is led by tenure-track Professor Maurice Döstermann. Here you can also see our fellow researchers, together with whom we have developed the research that we will present today. We are an interdisciplinary team with backgrounds mostly from architecture, but we also have mechanical and electrical engineers in our team, which you will see is quite important for the way that we develop our research. So the motivation behind our research comes from the overconsumption of resources in construction. As you probably know by now, the industry is responsible for a very large amount of extracted materials, nearly 50%. And on top of that, the linear economic model that we currently use creates a lot of waste. And for example, in the European Union, that accounts for 35% of all waste produced. So this raises a lot of environmental sustainability challenges, which is what we aim to address. And as the title of our presentation suggests, our research focuses on the circular economy. So we explore solutions within both the biological and the technical cycles. So when we talk about biological cycle in construction, we are talking about, for example, in our case, introducing innovative renewable materials. And when we talk about technical cycle, we are talking about how we can use reclaimed materials, but also how we can design building systems that can be reused or recycled. For example, we explore ways to expand the use of bio-based materials in construction. You can see on the left, one of those that we use is willow, along with earth-based materials and reclaimed materials, in particular reclaimed timber. And what connects all of these topics, the common thread is that our research works with materials that are non-standard or not standardized, which means that we have a lot of homogeneous traits or highly variable properties. And this is something that usually we cannot deal with within the realm of construction. So what we focus on is on how we can leverage digital techniques to manage complexities of these materials and to develop new methods that can help us overcome the current limitations. That can be fabrication limitations or design limitations. And our aim is to eventually introduce them into construction relatively quickly. And as part of this aim, you will see that our research evolves from experimental to applied, and we try to deal with all aspects of construction and architecture. And we do this with a lot of research demonstrators and with a lot of professional figures from different fields. And we then fabricate these research demonstrators in our lab together with our students. And coming back to this slide, today we'll walk you through two of our research lines and their progress so far. The first focuses on willow, a rapidly renewable material, and its combination with earth. Daniel will be presenting this. And the second centers on our research into reclaimed timber, and I will be presenting this one. And with that, I'll let Daniel take it from here.
Thanks, Erik. Yeah, also hello from my side, or good afternoon here in the European time zone. I'm going to show you or walk you through our research from the last 3 to 4 years that is in regard to fast regrowing materials, such as willow and also earth. Erik is going to walk you through our wood research and wood research into reclaimed wood in particular later. But the slide that I want to start with is that even though wood is a very nice building material that is through all the history like widely used and for our building and construction, the supply and demand don't really meet each other for the next future. So meaning that our industry at the moment requires much more wood than market can supply, and that is also healthy for deforestation of our forests. So regrowing materials in that sense, for example, willow that I showcase just in a second, can be an answer as a quickly regrowing material that just not has this cycle of, let's say, 10 years that a regular tree would have, but that is so fast regrowing that already after 1 year, there is some structure that we could also use for architecture. So the way I walk you through is chronologically. Also, our professorship is rather new. We started in 2021, exactly when also COVID hit, and we started with a master studio that did the first exploration into fast regrowing materials on the example of willow. Here you see a group picture of our students together with us researchers and a lot of manually mock-up models in which we try to explore just properties, configurations, and any kind of spatial structures that we could develop coming from this natural material, willow. I'm not sure if you're familiar with willow in general. So looking at this picture, maybe not in particular, but looking into these pictures, I'm sure that every one of you has already seen them, either in a basket or in historic buildings. So the way that we started also this studio is to do a good look back and to see how history, and especially construction history, has used such natural materials. They are available for ages already. And at some point, it feels a little bit like our construction industry has also lost of traditional materials and lost the way of traditional ways in which we apply them. So our aim, let's say at DDF, is also to take our inspiration from methods or construction principles that have already been done, but we try to use digital technology to develop them into also something new. You see here some exploration that we did with the students, starting from just one cell structures to multiple cell structures to also becoming more spatial structures. And from these manual tests, we rather quickly went into the digital fabrication, and we asked ourselves the question about this whole process of manually weaving willows is a really time-consuming process, and neither the labor nor the time is available at these days. So it has to be some kind of workflow that is also digitalized, that can be optimized, and become, in the end, in this way, time efficient. On the left, you see the first machine, let's call it, that we developed in order to place complex configurations of these structures, you can think of it a little bit like a 3D printer. So it's able to, in a specific path that we decide before, to lay down these willow fibers and then layer by layer just put them on top of each other and create these complex structures that you see on the component here in the background. The way we did it is, of course, using Rhino, using Grasshopper, trying to inform this in a also structural way that has been informed by all the research that we did in the studio before. And as a result, very quickly jumping into this one-to-one scale that we do at our professorship, and we think is really is a good way to early on experience maybe difficulties that could come up in the real applied work later. The examples you see here is on the left, for example, a beam that was a span of 3 meters. We have a wall segment that could also be a result of that, or a completely free woven willow column. Yeah, so already at this stage, one could say that we identified these 3 very characteristic building components, a beam, a wall, and a column, from which you could already think or go into a lot of different applications for the built environment. Going from there, we had a follow-up project that was for a local festival here. So the aim was for a music festival to present, first of all, our research, but also to give the audience a place to sit, to inform a little bit about the way or about the research that we are doing at this moment. And we looked into material combination of willow on the one hand and also on the natural material of earth. That's the second point that we're also very interested here at the professorship, is the hybridity of materials. So not using just the pure materials, but looking into ways and configurations of how we can combine different materials and out of this hybridity just make a stronger component. The way we designed this here was also with a focus on prefabrication. It was with a focus on thinking on component level. So how could such a building component out of willow and earth geometrically, first of all, look? How could it come together? How could it interlock? And maybe coming from this picture that you see here, which looks very artsy, was of course also because it was an arts and music festival, but looking at this slide, you see already that there's a lot of computational design and a lot of computational workflows that informed, let's say, our structure in the end. So what you see here is on the base, that's the top 3 layers. This is where we combined it with earth, always in these zones where we had pressure force. And on the top, there was just a vertical flip of the whole structure in which we try to explore different kinds of patterns and depth and visibility that you could go through. Going more into detail of these components, you see that also like every layer, every fiber was informed, computationally designed and informed from the very beginning. And these kind of models would then also be the initial step that we use for fabrication. So these informations go into our fabrication setup, and then in the end, together, of course, also with a lot of help of the students here that work with us, form these prefabricated components that after this got transported onto site, assembled, and resulted in this very interesting first research demonstrator structure of this hybrid material out of natural fiber, willow, and earth. Coming from this more arts and exhibition kind of design, there was the next step for a federal gardening show here in Germany. That was in 23, in which we tried to go from the sculptural aspect of this material system into a more building-oriented system, namely walls. So the configuration you can see here, it was meant for visitors to first of all explore again this material system. So you have to imagine the Federal Gardening Show in Germany, the audience is rather broad and is a lot of different people. And it was a great opportunity just to inform them and get into touch with them, talk a little bit about our digital circular approach into construction. And we used Reground, that was the name of this project, as a demonstrator of how we could prefabricate wall elements out of willow and earth. And also use it, let's say, as a showcase of how these components in a circular manner can be used for the building application. We started from the digital model, used all our analysis tools that you probably also use, Karamba, a lot of, and then did the final calculations, final analysis, and use always this digital feedback on the placement of these different willow fibers. So on the top, you see one of the components exemplary, and on the bottom, how the different force analysis of these components also influence the laying of these different patterns and fibers and layers on top of each other. So in the end, they also respond to the structural analysis that we do for these components. For this project, we upgraded our fabrication setup a little bit. So we went to a rather large scale setup in which we were able to do components 1 by 2 meters. We upgraded it also in such a way that we don't use the single willow fibers, but we splice them together, which you see in a video in a bit. And then used also a machine the first time to fill it then with earth. I hope this video is kind of fluent when you see it. So you see the fabrication process, yeah, in which our 2D axis machine here is extruding the willow. And that's an interesting step in which we splice different willow fibers together into one, you could say, unlimitedly long natural fiber that is then laid on top of each other layer by layer. Also to point out at this stage is it's interesting that on the left-hand side, a beam, for example, that is not reinforced, loaded with the same kind of load as the beam on the right side, like is really less strong. So you could say this natural reinforcement, or the willow works as a natural reinforcement for these structures. And in our test, they are able to hold up forces up to 10 times or even more of the structural of the load. Coming from this, we went into the prefabrication of the different elements. We loaded them again, put them on a truck, and then with the crane assembled them on site. Coming back to the slide that I showed in the beginning of the design, and ended up with this installation that gave the visitor the opportunity just to walk through and experience also different kind of depth, different kind of angles, to see how this the spatial structure of the willow also works for different kinds of visual aspects, visual feelings. Exactly. So then from this, the next project, now we worked already in the artsy kind of aspect. We were sculptural, we had the wall structures. What we were missing was the horizontal elements, so namely the ceiling slabs. For us, a ceiling element is it's a very interesting building element, since it's in its use very scalable and can have a big impact into the construction industry. And in particular, what was our interest or research interest here was how this combination out of willow and earth could work also as a building system for ceiling components. Usually, if we start on the left, over the centuries, wood and earth, they have been used in ceilings a great deal, but the earth mainly as a filling. So that was for sound absorption, to give some mass to the ceiling components, but never really structurally. Then there was a development that the structural aspect could come from a geometrical shape, for example, structural caps. But what we would like to do, or what we tried to with this research, is to combine all of this into one building component. In a way that we try to reinforce the willow, as you've seen in the picture that I just showed with this beam, to use the willow as a rebar. You could compare it also to the steel reinforced concrete. In our case, it's the willow reinforced earth. So in a way that these components can also take loads in multiple directions, and not only in one as the cap, or not only as a filling, but they can take loads into several directions. So the idea here was, again, prefabrication, again, the material system out of willow and earth, and then have them as a component that can be prefabricated in a nearby company, delivered on site, and used into multiple kind of architectural systems. Here, for example, columns could also be a wood frame structure. It could be monolithic walls. So the way we designed it was with a minimum amount of wood. Also thinking back on what I said in the beginning, that the amount of wood and the supply and the demand don't really meet. So we try to use wood only where it's necessary. And we had these two thin wood beams on the left and on the right side of the components. Then geometrically, you see there's a kind of an interface between the willow baskets and also the wooden beams. And this all got filled with earth. And the nice effect of this geometrical design, first of all, and then the combination also with the willow, was that in the end, here you see the component, we were able, since it was filled, to get a component that was structurally loadable into multiple directions. I have a quick video, so it gives you an idea of how the filling process works at this stage, still manually. Now we're also working on automation for this. And since this was also a research that more and more was application oriented and we wanted to use it in the real world, we went through kind of extensive structural tests. And here on this video, you see just the moment of failure. And we were able to load our ceiling component here with 130 kilonewtons, which equivals kind of to 13 metrical tons. So it's quite a load for a building that gave us confidence that the development into this direction was really going somewhere, and that this material system is also promising in the configuration, let's say, for a ceiling system. Here you see some application that we envisioned. So it could be a modular building, it could be multiple story, it's highly scalable, and of course, completely circular and recyclable. One impression of how it could look like as an interior. And also here we are able to play with different kind of articulations. The way in which we lay the willow fibers could also give a design opportunity to architects and designers at this point. And it, together with the material of earth, it also has this a really nice natural feeling. The next step after this was then going into real world application, again for a gardening fair, this time regional, in which we developed, or we were able to develop, the project called Residence, which was meant as a research demonstrator for a multi-story building, but building on exactly these kind of research projects that I've showed you to this point. And it was the first time that we were able to go for a multi-story mock-up in which you could also not just see it as a ceiling component, but also walk on it as a ceiling component. So it consists out of multiple different also research layers. We had a facade that was robotically woven out of flux from a company here. We have a main primary load structure out of wood. So again, minimal use of wood. And then we produced altogether 12 of our ceiling components in our factory, in our fabrication research hall here. 4 of them completely filled with earth and also cladded, and the top one then open with willow, so you can get also an idea of the aesthetic opportunities, let's say. Here you see a picture of the finished result with the stairs, so visitors could also go on the first story and experience how to walk on these components. An image from the assembly, so the prefabrication in or not on site, and only the transportation, and then the assembly on site was a huge aspect that we tried to achieve here, and that was successfully done. Some images of the aesthetics, if you look at one of these ceilings from the bottom, and of course here's also different kind of finishes that you could apply on them. On the left, so the top stories, you see the pure willow. On the right side, for the ground floor, you see that also plastering it with, for example, earth or other kind of mineralic natural materials is a potential to articulate these a little better. Here's one impression of how the freely woven robotically flux facade also works together with shading aspects. And kind of summarizing the slides that I've shown you from the very early stages of manual research within a couple of years, going to one of these components. This is really what we are trying here at DDF to achieve. So from first exploration into really quickly going into one-to-one scale and just doing it, just applying it, and see what is maybe going wrong, what is nice, what can be improved in the next time, and then applying it step by step, developing it step by step for the next projects, going it with the goal to finally bring it into real-world application. And this is something that is in planning at the moment. So on the very right, you see the EBA 27. This is our international building exhibition. Hopefully, we're able in 2 years then to have also 2 full residential buildings equipped with our hybrid ceiling structure out of this willow reinforced earth.
All right. Now we move into the second research line, as we mentioned earlier, which is about reclaimed timber. And also in this case, we have hybrid building components made of wood and earth, as you will see. A little bit of context in our local context. So in Germany, we have 11.2 megatons, so metric system. But what is important is that out of this amount of waste wood that we have, 65% actually comes from the construction and wood processing industry. What we know also is that of this amount of waste wood that we have, a lot of it is actually recyclable and it can be reused. So in Germany, there are different categorizations for waste wood, and A1, for example, that is highlighted here, is waste wood that does not have any contaminants, does not have any coating, so it's very easy, immediately recyclable. A2, on the other hand, has some coatings, but they're not harmful, so then it needs a little bit of more processing, but it can be used. And this accounts, anyway, these 2 categories account to 88% of the waste wood that we have in Germany. However, most of it, although it is reusable or recyclable, is actually incinerated at the moment, and only 10% is being recycled. And when we talk about recycling, we need to introduce another concept, that is the wood cascading concept, that basically explains how we go from the forest to the wood products, to timber, and then how we get to incineration. What is really important in the wood cascading is that every time we have a step down, we actually have losses. And when we talk about construction, the biggest loss is the structural loss, because obviously any wood product for construction depends completely on the fibers. So if once we chip them up, then we chip them down into smaller particles, then we are losing those fibers, therefore we are losing also the structural capacity of the wood. So what we want to focus on, what we wanted to focus on when we talk about reclaimed timber, is how we can basically reuse the components. So we can create one or multiple life cycles before it continues being cascading into this process. So here is showed with a small arrow, but it's really important step that we want to focus on. So what are the barriers at the moment in using waste wood? So what I mentioned earlier in the beginning as well is the complexity. We have a lot of non-standard and irregular sizes. We don't know a lot about the qualities. They are obviously degraded qualities, so we kind of need to know if we can actually use the pieces. Compared to the sawmill wood, we also don't know what wood species they are and what types they are. And we also have a lot of contaminants. That means either coatings, but also, for example, nails in them. Obviously, there is also a problem in the supply and demand. We don't know when we get certain types of waste wood. And the third big barrier is also related to perception, knowledge, and awareness. Some people might reject the waste wood because it is waste. In what way can we contribute to solving these problems is basically, for example, the fact that we have a lot of non-standard and irregular sizes. We can digitize those pieces, so we can reconstruct them, and we then can use what we are good at, which is computational design, to deal with this complexity and create strategies that are made on purpose for these wood pieces, waste wood pieces, then thanks to what we usually do in computational design, that we connected to the digital fabrication, we're then able to scale them quite easily into production. And the last thing, but not least, is obviously that, for example, we as architects are able to create a design language that makes it more acceptable for the general public. So these were kind of our aims. And I now walk you through some of the projects, also in a chronological line. So this was one of the first ones that we did. In this case, we started from waste wood coming from pallets. And the aim was to create a workflow that goes from sourcing to digital design to digital fabrication with augmented reality. What also we are using, and is quite important, is wooden nails. It's the third picture from the left. And in this way, if reconnecting to the wood cascading concept, essentially we are creating a component that is made of only wood. And in this way, we are also able to recycle it later if it cannot be reused anymore. Here is a quick video you can see of how we use augmented reality to then reconnect what we input as a digital inventory. And the concept for this research demonstrator is based on these ribs that are extracted from the initial design and then are reinforced by cross bracings. And here you can see some impressions of the pavilion, which is obviously quite, as you saw also, this was, as we start new lines in the beginning, we are also quite free form, and then we try to move closer and closer to construction. At the same time, we were doing this with a design studio together with our students, where we looked into a few other concepts. Starting, for example, from a wall, and also a different kind of computational, although we still use the workflow that I showed earlier, here is a bit of a different computational design workflow. So in this case, I think it's quite obvious. It's a nesting type of design approach, which is what we usually use, for example, when we use CNCs or laser cutters, and we need to compact a lot of pieces into one piece of wood that we need to cut out. But we also try to expand this concept into three-dimensional aggregations and into creating, for example, linear elements, or again, also a floor slab that works with earth and uses the irregularity that comes from the waste wood to actually create an interlocking that is based on geometry for the two materials to work together. So the underlying concept is the one that comes from the bin packing algorithms that are algorithms that are used often in the container industry or the packaging industry. The basic concept is that basically you have a volume and you want to be able to fill a lot of different sized packages into this volume. Usually you want to minimize the space that is left. But rather than this optimization, our focus was on the fact that you can use a lot of different geometries and it gives you a lot of different solutions. It is based on an iterative process. So you start with one package and then you start accumulating more, aggregating more and more packages. And essentially every time you change the order, you get a new solution. And that for us was what we wanted to use for our system. And we adapted it to what we have. So we have an inventory that is quite varied. Then we want a building component, and we have a few parameters that we want to change. I quickly show you kind of how all the concepts that I showed, the design that I showed earlier, are based on this basic concept where we start aggregating on a first layer, for example. Then we create more layers where we subtract the geometries that currently exist, and we continue aggregating until we reach a final component. And this allows us to create a lot of different geometries as well, a lot of different construction types. But what we decided to focus on was, and this we continued in another studio, getting closer and closer and with more details to construction, was on the floor slab. So as I mentioned earlier, it is based on the geometric interlocking between the two materials. So normally when you have a beam or a floor slab, you have this problem of the shear interface. I mean, you have normally compression on top, tension on the bottom. And when you have two materials like in concrete wood, you have this shear interface, which is usually conventionally solved by integrating screws, metal screws or metal plates. But that for circularity can be quite challenging because then it's very difficult to separate those materials afterwards. Whereas in this case, when we use this geometric interlocking, it's quite easy to then separate the two materials. And that's also the base concept that we use for the wheel of earth. Basically, earth can be just dismantled as far as it's not baked or anything, then it's easy to be taken apart from the material that is connected. In this studio, we looked into a lot of different parameters and how they also give a certain geometrical articulation in the components that we then apply to a one-to-one prototype. And we looked into how the whole different parameters come together. At the same time, as you saw earlier for the other research line, we always look into how we can then apply them to construction and also architecturally how they would work. We then continued with our latest research demonstrator in this research line, which is called Terra Timber. Here we applied a few of these concepts that we had. So you can see the floor slab, you can see the wall, and we also had a frame structure that is made of with interlocking joinery system rather than with metal joinery. So it could be easily disassembled or reassembled. As usual, this research demonstrator, as you saw earlier with our residence project, we try to imagine them as part of a bigger building, so then we could later scale them up. But with Terra Timber, what we wanted to do, earlier we explored a lot of different options, but what we wanted to do here was to really go systematically from the sourcing to the digital design and to the digital fabrication. So we started from a very specific type of inventory, which is industrial offcuts from a company that makes prefabricated houses. It's a bit of a reduced complexity inventory because in this case, we don't have a lot of the problems coming from the quality of the waste wood, but it was good for us to have a starting point. We then use photogrammetry to reconstruct these pieces. So we are approximating the contour of the pieces. And you can see on the bottom right, kind of what our inventory looked like. And in this way, we're also labeling all the pieces as we go, so that we have basically a physical and a digital inventory that then we use to look into different types of designs and evaluate them, seeing how they worked, not only aesthetically, but also in terms of fabrication and in terms of structural design. And we eventually landed on this configuration that takes principles from diagonally laminated timber. As you can see, we are using different angles for the different layers. And we are calculating where we need to use, again, we're using wooden nails as in the previous project. And we are calculating where they need to be placed. And essentially then we use again augmented reality to reconnect the digital to the physical. So in this case, together again with our students, they would see what is in the screen, the TV screen, and they are able to reconstruct what is in the digital through augmented reality. This is one of the components before we fill them with earth. And you can see a little bit on the left, also our design intent is creating kind of a surface that is kind of flat on the bottom, although alternating with different layers. But the right picture is instead taken from the top, where you can see this very patterned surface. That is what I mentioned earlier, is what this irregularity that comes from the process is what we use to create the geometrical interlocking with the earth. So this is our final component, which for the moment we tested just to make sure that it's safe to be used as a construction element for the research demonstrator that we created. But we will go further into the testing later as well. We then bring these components on site, we assemble them, and here you can see some of the pictures from the pavilion that we created. And you can also see some of the details, which gives quite clearly that we are embracing the material, this waste wood, and the bottom-up approach that we use in the design to also create a design language with it. Obviously, there is still a lot that we need to explore in terms of scalability. And this is something that we are working on also at the moment, both Tanya and I. So the next steps are, some of the steps that we're working on are, for example, using image recognition to even extract more data from the reclaimed wood that we have. We are also looking into having more precise digital design models that are based on rules that we're working together with structural engineers, so that we can really get step by step into a closer iterations for construction. And one very important part is that we believe that automation for this is obviously very important, because it's a very complex inventory of materials. Would be really difficult to work if we have to do everything manually. So at the moment, what we're working on is also to use robotic. We have now our robot in our fabrication lab, and this is what we're working on at the moment. And with this, I will actually conclude. You can obviously open to questions at the moment, but you can also find more information on our website or on our social media channels. Thank you very much for listening.
Thank you so much. It was a very interesting and amazing lecture. And wow, yeah, it's very impressive. I can't think about that. I'd like to ask anyone who has questions to come up here and share their thoughts with us. Anyone? I can start. So, what I've seen is that so you're using wood, reclaimed wood, with I guess like earth-based molds. So I have a feeling that because you also do the prefabrication, I have a feeling that this would be a little heavy for like transportation. So my question is, are you also seeing in the future that you would also construct this on site, especially that you're developing the like the assembly using robots, and probably you can use it, I mean, do the assembly using mobile robots, and then probably like in the future when you do that on site? That's one.
Yeah, I think so. Maybe I start and you can join in. We are looking into the different options. I think the only thing with earth, it can be a bit complicated to do on site. It is true that it's quite heavy. Although, for example, in the next iterations, we're working on reducing the depth of our components. The problem with earth is that it takes a long time to dry. So to do on site, it can be a bit complicated, especially because then we need to deal with the weather or any conditions that we find on site. So in a way, prefabrication helps us a lot with earth, because we don't have to deal with that. We know that we can control the environment that we are in, and that helps a lot with earth-based prefabrication. That's currently what a lot of the earth construction is, but it's true that there is a potential, especially if you have a multi-story building and it's already covered, to do it on site. And we will definitely look into that. I think in terms of wood, we are also looking into if to do online or offline fabrication methods. At the moment, our method is very offline, right? We scan the pieces, we have the inventory, and then we reconnect them. But that requires a big inventory, which can be a bit complicated. What we're looking into next is also if we have a very small inventory and then we just do it, for example, with that small inventory, and then it needs to build according to that small inventory, which could work well on site as well.
Yes, exactly. So I think except the fact that Earth just needs this drying time, the amount of inventory and the amount of pieces you just need to handle can be challenging for construction sites. But as Erik is pointing out, so we believe that going into an approach which is more designed by availability, let's say, over a fully equipped inventory, this can be really accelerating in this process.
Exactly. And also, do you think that you would probably have the opportunity to do that as well with the fibers, like leaving the fibers on site as well? Or
yes, I think the same logic or the same argument at this point applies for the willow reinforced components. So the biggest key here is this drying time, and drying time in terms of natural earth means at least 6 weeks. And if you imagine a really big building, that also requires a lot of space that usually is not there if you're not in the rural landscape somewhere. So for this reason, we think that the prefabrication here is the way to go. Nevertheless, there's also potential to use reclaimed wood on site, but maybe then in different configurations.
And maybe adding another layer that is separate to this is also the difference between what we did for the willow and what we're going to do now with the robots for the reclaimed timber. Is for willow, we created our own machines that is quite cheap, a lot cheaper than having a robotic arm, right? But that was one of the aims, that we would be able to basically replicate these machines somewhere else. So that we don't even need to bring the robot or bring the machine there, but it uses components that are quite easily accessible for anyone, everywhere, and that could be replicated. So in a way, in the willow, we also looked into how could we, instead of moving the machine, we actually make new machines there. With the robots can be a bit more difficult, especially because it needs very precise calibration, and it's difficult to, obviously there are mobile robots, but they're also very expensive. So in a way, we also looked at this social aspect, let's say, of how we could be more open sourced through our own fabrication systems.
What's up, guys? My name's Gabe. I appreciate the presentation. I also appreciate the type of research that you guys are doing. I like working with reclaimed materials and also incorporating the traditional construction methods as well. But my main question to you guys is, what's the biggest challenge you guys face when working with reclaimed materials, and how do you overcome that in means of fabrication, constructing it? Like, is there any failures, because, sometimes the reclaimed materials aren't as strong. And so you have to filter through a lot of different types. So just like the biggest challenge and how you overcome that.
I start with design, then Daniel can explain a bit more on the fabrication. So that is one of the biggest challenges for reclaimed timber. That's also correct. On the fact that we would never be able to, although through what we're doing now, through image recognition, we can start structurally grade the materials. So we can understand, for example, if there are degraded qualities, the fiber directions, and all of these can give you a quick understanding of how good a piece is. But we will never know what is happening inside. So there is always a huge part that is unknown. What we do through design, and this is also what kind of you can see, maybe I actually did not explain it, but obviously these are very massive pieces, but that is part of our concept because it's meant to be redundant. So even if some of these pieces fail, there is enough redundancy within the component that the whole component will not fail. So that's how we approach it from the design side. And then obviously there are a lot of complications in terms of tolerances in terms of fabrication. And I think Daniel.
Yeah, exactly. So maybe starting from a state of the art on standardized timber. So if you have standardized timber, you know exactly the geometry, you know the roughness of the surface. If you put it on the table, it's really flat. This is a material that robotically can be used fairly easy. Yeah. So already a lot of research and structures have demonstrated this. But if it comes to reclaimed materials, as you point out, there is unknown, there's uncertainty, there's heterogeneity in surface, there might be a little bit crooked, there might be failures in terms of there's a hole, there's a nail, and all these kinds of obstacles. First of all, these are different to tackle, yeah? Since a robot or an automized process would have to take all the steps that also you would have to take manually in order to work with these materials, right? So you would have to remove nails, you would have to check for cracks, you would need to check for maybe other problems in this material. Then going to placing is already tricky. At which side you can grab it, how you can grab it. Is maybe a vacuum gripper the right tool? Is a mechanical gripper the right tool? It really highly depends on then the geometry of the material. Then going to placing, the more irregular these materials are, the more tolerances you get the moment you work with aggregations. Layer by layer by layer, these small tolerances, they just add up. Also explaining these kind of adaptabilities to a robot is really, really challenging. Yeah? And also the main research focus, let's say, at the moment for us in working with these reclaimed materials. So I would say it's mainly just creating an adaptable process. Yeah? And adaptable means to a lot of different scenarios that can occur working with these reclaimed materials.
Perfect. Thank you so much.
Hi. So for my question was for the first project with the willow, was there a reason why you decided to focus on willow specifically, or is there another wood type that you were trying to test out?
Good question. The main purpose to decide for willow was the fast regrowing aspect. So willow, in the configuration or in the properties that you've seen it, with about, I don't know, what's that, an inch, maybe a third of an inch, so one centimeter in our metric system. This we can already harvest after 1 year. Yeah, in comparison to a tree, maybe after 10, maybe after 12. So this is why, this is one of the reasons that we used willow. And the second one is that willow here in our area is also considered to be a regional source. Yeah, so our, let's say, agriculture environment is a good fit for willow.
Okay, and I know you were talking about how you were trying to test out hybrid materials, like working willow with earth-based. Have you tried to test that out with different materials too, or just earth and wood for now?
So in the beginning, we looked into different materials. So the first, I think I was trying to get back there, but I realized it's a lot of slides. So in the first iterations that we did with our students, we also looked into different materials. But as Daniel explained, we wanted to focus in the beginning on also the local context and creating a sustainable systems. We wanted to look at what is available here. What we are doing now is also expanding this research. Actually, it's not what Daniel and I are working on, but some of our colleagues are looking into other contexts. For the moment, they're looking into, for example, working in Ghana and how we can use the local context and kind of apply some of the principles that we found from this research. I think you mentioned if earth or other materials, maybe. Yes. So for us, it was important that, so the point with these materials is that often they're on their own, they're not structural. So we needed one additional material that could hybridize with them. And ideally, they create a hybrid system that is better for both of the materials. And in this case, it works because willow works well for tension in earth, and earth gives the stability to the willow that we need. But earth, we decided earth because earth is a very circular material, so we want to focus on that. The point with earth is that we are able to, concrete, you cannot really recycle it, right? Once it's mixed and dried, we can break it down into smaller particles, but you cannot really reuse. With earth, we wanted to use earth because it really allows us to recycle the material at the end, reuse the material in theory, because basically we just either use water and you break it down back into the particles, or you literally break it into the particles, and we're then able to reuse it as it is, straight into a new material. So for us, it was really important to create a circular system, so this is why we ended up with this decision.
Thank you.
I have a question. I see that throughout the process, you're also generating a lot of data sets, right? So like ranging from the data set that you create for researching the material and the raw material. And I saw that you were also using photogrammetry to scan and then sort the materials. And then obviously a lot of design data is also created, and also a lot of fabrication data is created. And partly because maybe AI and machine learning is becoming a trend, but partly because you're creating a lot of data. Do you see a tangible and let's say impactful implementation of AI and machine learning in what you're doing? Have you done that? If yes, could you provide some examples? If not, how do you see in the future this can be more integrated as part of your workflows?
Yes, so we are working at the moment with on how we can use AI and machine learning. As we're working both on reclaimed timber now, mostly. So one of the first one is on sourcing, as I mentioned, is how we can implement image recognition, for example, for the sourcing of the wood, and we can extract more features that help us understand better what type of material we have in front of us. Another one is also on the bin packing. So one of the problems with bin packing, let me go back to the slide quickly. Here.
Switch the screens.
Yeah, sorry. I'm showing you the wrong screen. So for bin packing, one of the problems is that it really depends on the order of the pieces. So every time we change one element order, so we swap one element, it will give us a completely different solution, which basically creates a design space that is huge. And this also does not allow us to optimize easily, because it's not an obvious, the solution is not obvious compared to what you're doing as an input. So in a way, we are also looking into AI solutions for this, in terms of how we can actually use them to better understand our design space without having to optimize in the standard way. And finally, from the fabrication point of view, we are also looking on how we can basically let the robots kind of learn how to deal with the tolerances that we find within the system. So on the fabrication level as well. We are still at the beginning of this, but that's one of the research lines that we are currently working on as well.
Yeah, exactly. So I don't find the slide, the one with the AR emplacement for Terra Timber.
Yeah.
But I think AR can become really, really interesting. What Erik just mentioned last in this adaptable fabrication. So if you consider, for example, a craftsman placing reclaimed materials on top of each other, yeah, and we film this and we create a data set in which we just we do it how we would do it as a human. Yeah, we explain it maybe also with voice as an additional data layer, and then a machine can learn from this, or an AI can be informed, and this can be transferred to also the robotic fabrication in the end. So, for example, I just comment the way in which I would put the pieces in this picture together. Yeah. So I take my piece, I say I rotate it because then I overlap with the next two pieces. I put my nails in a way that I will at least shoot through coherent 3 layers underneath. I took this side because it was the better surface. I didn't shoot my nail here because there was a knot. You know, these kind of already of information. This you can feed it into a system that can learn, and that can also, we believe, help in the end to also inform and automate this process.
Wow, thank you. It was a very great discussion. And thank you for sharing your time, sharing your research with us. I would also wanted to remind everyone that we're going to share this recording on DARS YouTube channel. So tune in, and if you had any further questions, just let us know so we can. Yes. Thank you so much. Thank you for your time.
Thank you.
Thank you. Thank you once again for inviting us. It's really a pleasure. We both, actually, we didn't mention it, but we both studied in Delft with Sina. So long time that we actually know each other. Thank you again.
That's some fun.
Thanks, guys.
Yeah.
Thank you so much. Have a great day.
You too. Bye-bye.